Now, if we have a linear drag force of the form drag force equals negative CV, which is then negative C times x prime squared times x prime, the equation changes. Now, how would we get a drag force? Well, a pendulum swings back and forth. It encounters air resistance. It's swinging slowly. That air resistance is pretty much a linear function of its velocity. The faster it's moving, more drag force. Now, if you have a pendulum moving much faster where you get some turbulence, then this is no longer going to work. This is purely for a case where the air moves around the pendulum in a laminar manner. You have a laminar flow. In any case, it's fairly easy to understand then that the drag force, I don't know why I have an equal sign there, but hopefully I didn't confuse anybody in class. Drag force is going to be negative C times the velocity, because it's going to be in the opposite direction. If we're moving this way, the drag force is back this way, minus, okay, this is just the drag force. I needed the equal. And C times the velocity is then negative C times x prime. Negative C times the velocity is negative C x prime. Okay. So that with linear drag, the net force is going to be, well, again, you have the negative K over mx, you have the restoring force, and you have a negative C over m x prime, which is the drag force. Well, the negative Kx is the restoring force, negative Cx prime is the drag force. That's equal to the net force, which is mx double prime, and I've divided through by the m here. Rearranging this, we get the equation x double prime plus C over m x prime plus K over mx equals 0. So now x is, I just used alpha here. It's not a particularly good letter to use, but we're going to use it. X is some scalar multiple of e to the negative C over 2m plus square root of C squared minus 4km divided by 4m squared. Now, there's some details here, but you just plug this, you plug the coefficients here into the quadratic formula, and you get this, where the 4m squared is just the square of 2m, but I've put it up here under the square root sign so that I could rearrange everything, and actually I really didn't need to put it under the square root sign, but it could be put there. I've kind of taken it out from under the square root sign when I factored out the 1 over 2m. So we have then e to the negative C over 2m. We factor out e to the negative 1 over 2m, and then we have negative C plus or minus the square root of C squared minus 4km, all multiplied by t. That's our exponent of the exponential. Now, the nature of this solution depends on whether C squared minus 4km, this quantity under the square root sign, is positive, negative, or 0. Okay, if the discriminant is negative, we get x equals e to the negative C over 2m t. Just factoring that out. I'm not going to explain how that's done. Everybody should know how that's done. So it's e to the negative C over 2m t multiplied by then e to the 1 over 2m times this discriminant, times the square root of the discriminant. The discriminant is negative, and actually I do need to say a little something about that, because when I write the solution down, I change the signs. I change this to negative C squared and 4km. Here I have cosine of negative C squared plus 4km, all divided by 2m times t. Let me pause and write a couple of things down here to explain that a little more thoroughly. Okay, if C squared minus 4km is negative, according to discriminant is negative, then we have a square root of a negative here. I can write that as a square root of negative 1 times the square root of the negative of this. So just changing the sign here and writing it with the plus first, we have 4km minus C squared. A little hard to see the C squared there, but we have the square root of negative 1 times the negative of this, and e to the square root of negative 1 being I, this rearranges then to I e to the square root of 4km minus c squared, a little bit easier to see here, times t, and of course we have the 2m in the denominator. Okay, I wrote a couple of things down here, but I also corrected something really ignorant that I did here because I saw that it wasn't going to lead to what we were going to do over here. I could have edited that out, but I'll leave it in. I had an I times e to the etc. And it's e to the I times that. Obviously, the square root of negative 1 is in the exponent here, and I was kind of getting ahead of myself and making a mistake at the same time. So it's e to the I times this, and of course we know that that's going to be equal to the sine of this plus the cosine of this plus I times the sine of this exponent, which is going to lead us to the cosine of, well, the exponent is 4km minus c squared over the square root of 4km minus c squared divided by 2m. And that's what we have here. So we have some multiple of the cosine of the 4km minus c squared over 2m, and the sine of the same thing, multiplied by another constant. We've already factored out the e to the negative c over 2m times t, which can be done in a very straightforward manner that I'm sure everybody can understand. Of course, if you have questions, let me know. Okay. Now, x can be expressed in this form, and then we can express this as sum a e to the negative c over 2mt times the sine of this argument plus theta naught. And what we then have is we have sort of a harmonic motion. It's not a simple harmonic motion. The sine, though, gives us something like the sine of omega t plus theta naught, but now omega is a little different than it was before. It's the square root of 4km minus c squared divided by 2m. Now, if c equals 0, this reduces to what it should, because if c equals 0, that means you have no drag force. And if you have no drag force, then you just have the case that we had earlier, as a simple harmonic motion without this term here. And that gives us omega equals square root of k over m. So if c equals 0, that's what we get. And of course, if c equals 0, e to the negative c over 2m times t is e to the 0, which is 1, and we get just a times the sine of omega t plus theta naught. But now, again, if we have a non-zero c, we see that that does two things. It changes our angular frequency somewhat, and it also gives us, it superimposes on that simple harmonic motion that we would have if this was the only term. It superimposes a decreasing exponential on this motion. So that's what happens if your discriminant is negative. We'll do a little more analysis of this shortly, but there's your function. Again, basically sort of a simple harmonic motion with angular frequency omega that's decreased a bit because of the drag force. In other words, we slow down the motion a little bit, or maybe a lot, and an exponential decay because, of course, the linear restoring force, or the drag force, is dissipative. It's going to dissipate energy, so the oscillator is going to have to lose energy. Okay, now of course that'll apply to a pendulum or a mass on a spring or any system where you have a linear restoring force and a linear drag force. Okay. Now, if the discriminant is positive, what's that do? Well, you can verify that the solution can be written like this. All I've done is, again, I've already factored out the 1 over 2m here, so I've just rewritten what I've got here, except here I have the plus or minus, and here I separate it. I do the plus case times one constant, the minus case times another constant. Now, the interpretation of that is that you have exponential decay in both cases. C squared minus 4km, the square root of c squared minus 4km, is less than the square root of c squared, which means it's less than c. So you have negative c plus some term that's less than c. So this is still going to be negative. So we have an exponential decay here. We have an exponential with a negative coefficient of t. Now, here we have the same thing, except that here we're subtracting the square root of c squared minus 4km. Well, what happens when you subtract the square root of something that's less than c certainly, but yeah, maybe pretty close to c, maybe pretty close to 0. The biggest or the smallest negative, the negative of minimum possible absolute value here would be negative c. So you'd have at least an e to the 1 over 2m times negative ct. And it could be, if k is small, close to negative 2ct. This negative coefficient has a greater magnitude than this negative coefficient. Both imply an exponential decay, but this implies a slower decay. This implies a faster decay. So you can, by solving for the constants in terms of whatever the initial conditions happen to be, you're going to automatically adjust this to some mix of a slow decay and a faster decay. In any case, you're going to have an asymptotic approach to equilibrium, because this term, as t gets large, approaches 0, and so does this one. You have negative coefficients. This one approaches 0 a lot more slowly probably than this one, but they both approach 0, so you're going to have an asymptotic approach to x equals 0. X equals 0 being the equilibrium position, you have an asymptotic approach to equilibrium.